Okay, have you ever looked at the sheer size of modern frontier-level AI models and just thought, there is absolutely no way this is ever going to run on my local device, right? I mean, we're talking about massive models that need whole racks of specialized servers, hundreds of gigabytes of VRAM, and, enough electricity to power a small neighborhood. Well, welcome to the Explainer. Today we're diving into a total masterclass in computational illusion that completely flips that script. Because this is kind of the ultimate holy grail problem of modern computer science. Seriously, how do you fit an 8 billion parameter artificial intelligence into a smartphone? Just think about the severe hardware limitations of mobile devices for a second. You've got tight thermal constraints, tiny batteries, and a really strict cap on active memory. Trying to squeeze a state-of-the-art multimodal AI into that kind of environment, it's literally like trying to pack a blue whale into a bathtub. It just shouldn't fit. And yet, 2 gigabytes. Yeah, 2. That's the shocker right there. Google's newly unveiled Gemma 3N model can actually run locally, effectively, and brilliantly with as little as 2 gigabytes of RAM. It's basically the ultimate illusionist when it comes to resource constraint. It packs 5 billion raw parameters in its smaller E2B version and 8 billion in its larger E4B version, but it somehow operates completely smoothly within the memory footprint of a much, much smaller model. So how on earth did they pull this off? Well, here's our roadmap for today. First, we'll meet Gemma 3N. Then, we'll explore its 3 main architectural magic tricks: elastic sizes, memory hacks, and compute hacks. And finally, we'll look at the era of edge AI. Section 1, Meet Gemma 3N, the multimodal illusionist. So, unveiled at Google I/O 2025, Gemma 3N is an open-weight model engineered specifically for offline edge deployment. And it's natively multimodal, meaning it processes text, images, and audio right out of the box. But to actually do that, the engineers had to solve a massive bottleneck. If you break down the transformer architecture, feed-forward networks, or FFNs, are just incredibly greedy. They gobble up over 60% of a large model's computational and memory resources. That right there is the exact bottleneck our first magic trick is designed to completely dismantle. Moving on to Section 2, the Matryoshka doll architecture, elastic sizes. This first major innovation is, frankly, a total eureka moment in AI design. Picture a classic set of Russian Matryoshka dolls. You open the big one and boom, there's a smaller, perfectly formed one sitting right inside. Well, that is exactly what the MatFormer architecture does. The smaller, lightweight E2B model lives entirely inside the larger E4B model. They literally share parameters. The FFN blocks are nested together. This means developers don't have to train a 2 billion parameter model and a 4 billion parameter model completely separately. The training strategy jointly trains them all together, so you can just extract the smaller model without any retraining or messy post-hoc pruning whatsoever. It's brilliant. And that brings us to the true superpower of elastic sizes. Because of this nested design, we get this thing called Mix'n'Match Inference. You're not just stuck choosing between the big model or the small model. You can actually dynamically mix granularities at different layers of the neural network. Like layer 1 could use a small configuration, and layer 2 could use a much larger one. For a 24-layer model, this creates over 2.8 trillion possible submodel configurations post-training, trillion with a T. It means the AI can instantly adapt to whatever memory your specific device has available right at that exact second. Which leads us to Section 3, shrinking the memory footprint, memory hacks. Now, elasticity is awesome, but it's really only part of the equation. An 8 billion parameter AI still has massive token embeddings that threaten to completely overwhelm a phone's tiny VRAM. Standard execution usually tries to cram everything into the high-speed device accelerator, right? Like your mobile GPU or TPU. But Gemma 3N uses a technique called per-layer embeddings, or PLE. PLE does something really smart. It decouples the heavy token embeddings from the core model. It actually offloads them to your device's much more accessible CPU memory, computes them over there, and then seamlessly merges them back into the transformer's pathways at runtime. This clever little detour is exactly how the 5 billion parameter E2B model only requires 2 billion parameters to be loaded in the active accelerator memory at any given time. And speaking of clever memory tricks, we have conditional parameter loading. Since Gemma 3N is natively multimodal, it has these distinct modules, like a MobileNet V5 vision encoder and a universal speech model audio encoder. Think of it kind of like a modular Swiss Army knife. If you're only asking it to process text, well, it simply keeps those other tools folded away. It skips them entirely. You only pay the memory cost for the specific task you're executing right then. It's so efficient. Next up, Section 4, Smarter Compute with AltUp, Compute Hacks. Okay, so we've shrunk the model size and we've hidden the memory. But what about the raw processing power you need to actually run the math? That brings us to alternating updates, or AltUp for short. Normally, if you want to make an AI smarter by expanding its dimensional width, you have to compute that entire width in every single layer. It's a massive drag. But AltUp kind of cheats the system using a brilliant three-step sequence. First, it predicts an estimate for different chunks of the data. Second, it only fully computes one small subblock. And third, it uses that updated subblock to correct its predictions for the rest of the data. It's essentially widening the network's capacity without ever having to compute the full width all at once. And the resulting math on this is just wild. The complexity drops from a terrifying quadratic curve down to a highly manageable linear one. To put all that abstract math into everyday perspective, this efficiency hack is exactly why your laptop or your tablet doesn't literally catch on fire during generation. You get the intelligence of a massive, wide network, but the computational heat and battery drain of a narrow one. It's a total game changer. Finally, let's look at Section 5, the era of Edge AI, real-world impact. So when you combine these elastic sizes, the memory hacks, and the compute hacks, the results are pretty unprecedented. Thanks to these optimized architectures, the Gemma 3N E4B is actually the very first sub-10 billion parameter model to break a score of 1,300 on the LM Arena benchmark. That's huge. It handles 140 different languages, and because of that conditional parameter loading we talked about, it processes vision at a blazing 60 frames per second on edge TPUs, and handles up to 30 seconds of streaming audio natively. It's quite literally giving you cloud-level capabilities completely offline. This is just a massive leap forward for the Gemmaverse ecosystem, which already boasts over 160 million downloads. By making frontier-level AI fit into just 2 to 3 gigabytes of RAM, we're fundamentally democratizing access here. We're finally moving away from this total cloud dependency. Think about what that means. Your data never has to leave your device, it is inherently privacy-preserving, it's incredibly fast, and it's completely immune to internet outages. It scales seamlessly all the way from heavy enterprise computer vision pipelines right down to the phone sitting in your pocket. The constraints that used to hold edge computing back, memory, compute, and architectural rigidity, they've essentially been solved by these elegant mathematical illusions. The tools are now open, and they're available for everyone. So the only question left to ask is, what will you build with offline, private, frontier-level AI right in your pocket? Thanks for joining me on this explainer, and I absolutely can't wait to see what you create.